This video covers Kirchoff's laws of circuits. And there are two of Kirchoff's laws, and they are going to be useful for circuits that can't be simplified using simple resistor analysis and simple series and parallel analysis. The first of Kirchoff's laws is called the current-junction rule. We're going to look at it over here. Basically what it says is the total current entering or leaving a junction is zero. So if we draw a junction here, or a node, that's just a point where multiple paths come together. I1 is coming in, I2 is coming in, I3 is coming in. Kirchoff's law says if we add up all those, we will get 0. Now that doesn't mean all of these currents are 0. And if we actually solve this, we get I1 is equal to negative I2 minus I3. And so I1 is equal to the negative of the combination of these two. Now, those negative signs are okay. All that they mean is our directions are going to be off for some of these. That negative I2 means our current would actually be reversed, and that negative I3 might mean this I3 might actually be going in the opposite direction. But the total current entering is going to be 0 in this case. Now, it doesn't really matter what direction we draw our currents as long as we are consistent with our signs. So an alternative way of writing this rule, and this is the one that I often like to use, is down here. And here I've just drawn it a little bit differently. We have I1 coming in and I3 and I2 coming out. When we set it up like this, then we say that the total current entering is equal to the total current leaving. So we say that sum of the currents going in equals the sum of the currents going out. We get I1 is equal to I2 plus I3. Now again, it doesn't really matter whether we use this one or the other one. It really just depends on how we draw our arrows. And if we choose the direction of the current to be wrong, if our choice is physically wrong, then when we solve our circuit, we'll get a negative sign there that'll indicate the direction's actually in the opposite direction. And this law actually comes from conservation of charge. If we have a certain amount, well, current is just charge per second, so if we have a certain amount of charge going into this point at each second, it has to be, that same amount of charge has to be leaving each second. Otherwise, if that weren't the case, then we would have extra charge building up here, and we would have a lack of charge over here. So there would be some repulsion over here. And inside a conductor, if we have charge buildup, then it's just all going to kind of repel itself out. It's kind of a self-regulating system. So let's take a look at our other rule. This is called the voltage loop rule. And it says that the total voltage around any closed loop is 0. And this is how we write that rule. Sum of the voltage equals 0 around a loop. Here I have a little circuit. And there's more than one loop we can draw here. But remember that voltage is potential difference. That's the difference in potential between 2 points. And potential is a lot like potential energy. It's potential energy per unit charge. So it only depends on position. So anywhere on the same surface, you're going to have the same potential. Anywhere in this yellow section, you're at the same potential. Anywhere in this green section, you're at the same potential. Same for the other two colors. And that's because a conductor is an equipotential surface. So anywhere on here, we're at a constant potential. And that potential depends only on position. So that means if we start on this yellow surface and we take any path to get back to this yellow surface, we have to be at the same potential, which means any potential increases have to be matched by an even amount of potential decreases, which is the same as saying all of the voltages added up go to 0. And so what I've done is I've looked at all the possible loops here, and I've written an equation for Kirchoff's law here. Notice we have 3 possible loops. Loop ABCFA, that's ABCFA, this little loop here. And I've actually labeled the polarity of resistors here. I've labeled one side plus and one side minus to indicate that I think there's going to be a voltage drop if I go around this way from this end. And just like the current before, it doesn't really matter which polarity you choose. If we chose the wrong polarity, then we're just going to get a negative sign when we actually solve our circuit and get an answer. So our equation for the first loop, as we go around, if we start out at A, voltage of A is equal to, or voltage of A plus negative voltage across R1 plus negative voltage across R2 is equal to 0. And these are negatives because it's going to be a voltage drop. The same thing for our other two loops. This loop, voltage across B is equal to voltage across B minus voltage across R3 minus voltage across R2 is equal to 0. As we go around, we get to 0. We could do one more possible loop. We could go up VA, down across R1. Then we're going to go up again across R3 based on how I've drawn my polarities, and then down again across VB. And that all adds up to 0 down here. So that's that. There are two voltage laws, and we're going to use them to solve more advanced circuits like this one that have more than one voltage source.